Okay, so thank you so much for coming to my talk today for the SAERT 2024. My topic today is the application of visibility graph and the graph attention network for urban smart grid short-term load forecasting. My name is Bo, and I graduated from the PhD program of Department of Industrial and System Engineering of University of Miami, and now I'm a postdoc working for the University of Maryland. My talk today has three parts. The first part is research background. The second part is research methodology and case study. And finally, I will talk about the conclusion and the future work. So this is a typical methodology flow for complex system analysis. As you know, there are a lot of sensors and meters currently installing on the complex energy systems. Based on this sensor data, we can form a big data. Based on this big data pool, we can use different modeling and analysis tools to extract information and knowledge. Based on this information and knowledge, we could further optimize, improve the current system, or redesign the current system. As you know, the complex system is everywhere in our life. Our human body is a complex system. Nowadays, there are a lot of smart devices we are wearing to generate a lot of data for further analysis. And also the smart grid energy systems, there are a lot of sensors installed on it to continuously gathering the time series data. Conventionally, we prefer data that is linear, stationary, clean, and continuous. However, in the real world, the data are often non-linear, non-stationary, noise, intermittent, and switching. So here comes a nonlinear dynamical system analysis. The nonlinear dynamical systems are often difficult to solve analytically, and the components of this system are often interconnected and interdependent. As you can see here, this Rosler system can be described by these three mathematical equations. Based on these mathematical equations, we can gathering the time series data. And based on this time series, we can forming a trajectory in space to further study the underlying dynamical nonlinear system. One popular tool is a network, recurrence network or recurrence network graph. We converting the time series from the nonlinear dynamical system to network graph and use the graph topology to study the underlying system. In this research, we use the visibility graph. If there's no interceptions between these two time points bar charts, then these two time points are connected on the visibility graph. So by studying the graph topology and the graph statistics, we could analyze the underlying system. So nowadays, a lot of people are using the graph neural network to study the network, to study the network graphs. And we can use the output of the graph neural network for prediction, classification, and regression, and different regression tasks. The graph attention network, a variation of graph neural network that leverage the attention mechanism for feature learning on graphs. The graph attention network constantly outperforming graph neural network on similar tasks. And here is the attention steps, and that describes the underlying mechanism of the graph attention network. In this case study, we used the Panama power system data from 2015 to 2020, which are hourly recorded data. And in this study, we use the time features, weather features, and to predict the electricity load 24 hours ahead of the current timestamp. As you know, the electricity load from the smart grid is highly nonlinear and non-stationary. In this case study, we firstly extract new time features from the existing data time variables. Then we normalize this data and using a moving window size of 24 hours time step to intercept different data sections and converting these data sections to the visibility graph, as you can see here from this visibility graph attention network flowchart. After constructing the visibility graph, we use the graph attention network to modeling the visibility graphs, and the output is the load forecasting for the grid system of Panama energy system. So here shows our model performance compared to the conventional machine learning and the deep learning models, such as XGBoost, random forest, GBM, BiRST, LSTM, and so on. And our model performance is in this red box. As you can see here, our model achieved the lowest RMSE and MSE value compared to other models, and our testing time is also very short. So, and the plot down below shows our model forecasting compared to the actual cloud. As you can see here, our model can clearly capture the nonlinearity and achieve very accurate forecasting performance. In conclusion, in this research, we propose a novel approach for short-term load forecasting in urban smart grid. And the benefits to the smart grid is this tool could be used to optimize the power generation distribution and benefit the maintaining of the grid system stability and the renewable energy resource integration. In the future, we're planning to incorporate additional data variables into our model, and our model could also be extended to other energy systems